Today's webinar is going to be on control optimization and fan system tuning. So thank you everyone for joining us today. Just a reminder, a little bit of housekeeping to get started. Today's webinar will be recorded. Feel free to fire through questions as they arise through the presentation, and we'll endeavour to get to them at an appropriate moment or discuss them at the end of the presentation. Okay, so without any further ado, we'll get underway. So to start with today, we're going to talk a little bit about what we mean by fan system control in terms of an overview of what it is we're trying to do with the system. Then talk about direct versus indirect control, understanding what your control levers are. Then we're going to look at a couple of scenarios around single versus multiple outlets and single and multiple fans. I'm going to talk a little bit about some spillover benefits of system tuning and a few case studies along the way. So just to start off with today, if we consider our fan system and how it's controlled, so we might have a fan or a number of fans, and they're obviously generating some typically air movement. Could be some other processed gases, but in this case we'll stick to air. Feeding through to some system which might have multiple users or a single user, and obviously there's a certain demand required, and then obviously there's a supply that the fan is able to put out. You might have some reticulation as opposed to some fresh air, or it could be open, closed, or a combination of the both. But fundamentally, at any one instant in time, the system will be in equilibrium. Now, if it's not in equilibrium, that's obviously ramping up, ramping down, but ultimately, instantaneously, the fan must be supplying whatever the demand of the system is requiring, and if it can't, obviously the fan will only supply what it can, in which case the system may be starved of what it requires. But either way, at any one time, the system is going to be in what we call a instantaneous equilibrium, where the supply curve and the demand curve, otherwise known as our fan curve, and our system curve, it's where they intersect is where the system is going to operate. Now, any one time, we might, for a fixed speed fan with a fixed fan curve, we may move up and down this fan curve, and as a result, obviously our volumetric airflow delivered by that fan is going to change. But fundamentally, at any one given instant in time, the system will be in equilibrium. Now, it may not be a stable equilibrium. It could be a state of flux and moving around. It could be quite unstable, in fact, and you see this from time to time in a number of systems, both industrial, commercial, but ultimately at any one given point in time, that the system is operating where we have an intersection between our fan curve and our system curve. Now, within our system, we obviously have our fan, which is generating our airflow. We've got ducting that could actually be before and after the fan, filtration and all the rest of it. Then we have wherever that air is being used. It could be a cooling load, a heating load, could be a process airflow demand, could be any number of things, but fundamentally this is what we're wanting, i.e. a certain amount of airflow at a certain temperature and possibly a certain humidity. This is how we've got to get that flow in and out of wherever it's being used, and this is the driving force to make that all happen. Now, when we talk about the fan, we can directly control the fan itself, i.e. we might be able to manually adjust the speed of the fan, or we might actually have some sort of automatic control. Now, we could actually look at the speed of the fan, we could look at throttling the fan. There's a number of different options, but fundamentally direct controlling the fan as a way of controlling what goes in or out of the system. Now, we might actually alternately more directly control the airflow itself and then just expect the fan to respond. Or indirect control is where we use static pressure, so we might have a number of dampers in the system, and so that's where we're controlling the demand by virtue of controlling the pressure. And so if we go back to our system curve, what we're doing then is we're either controlling pressure, controlling flow, and then the system is going to respond. So the question you want to think about when you're thinking about your fan system is how many control levers do you have? Then of course the separate question is how many of those control levers do you actually want to or should you be using? So if we just talk about direct fan control for a couple of minutes, what we're talking about here is we can first of all change the fan curve, and this is where we will we can change the fan curve by changing the speed of the fan. We can do that by a VSD. We can do that with a pulley change, which is obviously a very incremental change, and obviously fixed step changes in speed based on pulley ratios available. And then of course other options, you could have the system fitted with a gearbox or some other mechanical speed controlling mechanism. Now the other alternative, which is a bit sort of another step again beyond just a pulley change, is you may actually look to trim the impeller or actually change the impeller. It might be to put a bigger impeller in or a smaller impeller. Now what's interesting, of course, something for you to think about, many of you out there have fans where they may actually be a little bit too big or they could be a little bit too small. One of the options that often isn't very well understood is you could actually potentially change out the impeller, maintain your same fan housing, and in a lot of instances you may or may not need to change the motor, but you can get a different size motor with the same frame size to fit on the existing fan frame. And so what you could do is you could put a different sized impeller in. Now what's interesting, of course, there are two main variations. We can add width to the impeller, or we can also add radius, i.e. the diameter of the impeller. And there's different pros and cons of doing both, and this is where it's important to talk to your fan supplier to make sure you're getting what you want. And I guess first of all, and we've talked about this previously, if you've done or completed good quality system assessments and measurements, you'll know exactly what you've got and potentially what you need. And then based on what you've currently got, you can infer with some decent analysis what you might need, and it could be the next size impeller up, either be in width or diameter or both. Now if you're unfortunate, you could already have the biggest impeller available for your fan size, in which case you will need to then go up to a next sized fan housing and so forth. On the other hand, you might find that you can actually get a slightly bigger impeller, and some fan suppliers out there these days are actually incredibly good at fitting a slightly oversized impeller inside the housing. They've got great techniques available now where they can work all sorts of magic, but strongly suggest you get some expert advice before you go down that path. So fundamentally, changing the fan curve, you're either changing the speed of the fan itself, or potentially upgrading, tweaking, changing the actual fan impeller itself. Now the alternative to this is we could actually change the system curve, and this is where we're using inlet dampers around the fan, which is going to reduce the net static pressure gain that the fan puts out to the system. What you're doing effectively is the fan is still going to produce what it's going to produce on the fan curve, but by throttling the inlet or the outlet, you're putting an extra pressure drop in the system, so it's shifting the effective fan curve. Now what you can do is you can do this quite efficiently with variable inlet guide vanes. If they're installed and actuated correctly, they can actually get a very good performance. Certainly at the upper end, you'll start to lose a little bit in efficiency at the lower end, and the sort of the 30% of full load, 40% full load, but up at 70-80% they're going to perform very, very well. Now you might just have a cheaper option, which could be an inlet damper or a butterfly, and you've seen the odd one around, or some of you may have, which is just a straight knife, which can be incredibly inefficient, does all sorts of nasty things to the airflow in the ducts, has a fairly high loss coefficient, but obviously very cheap, and a very crude way of sort of throttling the output of a fan. But fundamentally, when we're talking about direct fan control, we're either directly changing the fan curve itself, or indirectly by throttling the fan either before or after the fan, the effective output of the fan. But it's really about controlling or adjusting the fan as opposed to the rest of the system. I think I've just had someone query the sound. Everyone else seems to be okay. So hopefully if someone can verify that we're getting sound, that would be appreciated. And just on this point, we've had a question from Graham, who's asked in relation to inlet dampers on the fan, do they have a risk of adding noise to the system? We're going to talk a little bit more about this later today, but I wanted to pick up on this now, and it's actually a very good question. Thank you to those of you that have just confirmed that our sound's okay. Appreciate that. So just good to know that that is all okay. So in relation to inlet dampers especially, and also apply to outlet dampers, if you've got a damper that's causing a lot of disturbance to the flow, that is certainly going to create a lot of noise. Now, depending on the nature of the system, you may decide that that's what you need, but you then may need to look at an attenuator. And so generally the good advice is to do the flow damping properly as opposed to taking a shortcut, because ultimately you'll end up having to spend more money to fix it in the case of sort of controlling fan noise and so on. So very good comment, Graham, appreciate that. Yeah, so noise becomes an issue as you disturb the flow. Then of course it can also be a source of vibration, and with air ducts in particular, they tend to be quite large and often they're not as structurally rigid as you might like, and the consequence of that of course is if you disturb the flow has really good ability to excite large flat sheets of ductwork. And so that can then not only create noise from disturbing the flow, but then can create a lot of vibration that can cause and lead to other problems. So no, very good question. So if we look at what this means in terms of direct fan control, if we're changing the fan, we're looking at changing our fan curve. And so if we just sort of get our highlighter here, as we change the fan speed, we have a series of fan curves which is moving up and down our system curve. Now what we can also do is, if we use our dampers either upstream or downstream of the fan directly, what we're doing is adding a pressure drop into the system, which means we are changing the system curve. Okay, and so what that really means is you're going to move from this point here to this point here. So this would be where, let me just erase it so it's a little bit clearer. If you are keeping the fan curve the same but adding your damper, what you are doing is moving up and down here as you change your system curve, and your system curve is changing by changing for a given flow an extra amount of pressure. And so it's very important to understand that when you select a certain mode of control, that you understand what impact that's going to have on the system. Okay, so in direct and indirect system control, we can change our system curve, we can change our airflow, we could also change temperature, could be a duty change, will be demand based. Okay, we can change our static pressure, we can have multiple duct dampers around our various demand points, we can have multiple control points, primary, secondary, even tertiary control. But what you want to be very, very careful with understanding in your system where you have multiple control points is you need to be very careful to differentiate between fixed and variable set points. So some of those control points might be a set and forget sort of fixed control point. So you might have a damper valve on a multiple outlet into a fluid bed, for example, where you might have sort of 7, 8, 10 or more intakes, and you might have a damper on each one of those, and that's designed to be able to adjust each of the flows to get it even across the whole bed, and you'll obviously do that by varying the pressure drop across each of those damper points. And typically in a lot of manual applications like that, it's something that you'll set and then forget and won't actually then be continually controlling actively that set point. So when you're looking at a system, very, very important to stop and ask the question, okay, is this control valve, be it a damper, a butterfly, a knife, whatever it is this something that is sort of locked in once I tune my system, and then it's left in place, or is it something that's being actively controlled? Now, what's often useful from time to time when you're looking at a system, there may be a number of those points that have been set and forgotten about, and they may no longer be appropriate given other systems that have changed or been tweaked or modified. And so it is useful from time to time to go back and review and ask the question, does that system need to be retweaked, retuned, or is that actually still appropriate? Plenty of instances where a lot of those secondary and tertiary control points can actually be eliminated very carefully, which can do wonders for a system's performance. And what I want to iterate right at this point in time is that it's also very important to remember that every time you put a damper valve into a flow stream and you're damping the flow to control it, you are disturbing the flow and impacting potentially downstream on where that flow's going, be it a drying bed, a fluidized bed, some sort of reactor vessel. You are disturbing the flow, and they may actually adversely impact the efficiency and performance of the system that it's feeding. Okay. So sorry, just to go back here. So once again, in terms of our when we're playing with our system, the fan might be fixed, but then as we tweak these other dampers on the system, we're going to then obviously, as we've already talked about, move up and down that fixed fan curve. Okay, so what we want to do now is we're going to just work through a couple of very simple examples of how this all translates. So here's a simple application where we had a single fairly large fan with a single outlet. Now what was interesting with this particular system, we had a relatively modest total static pressure of 1.5 kPa. The fan was actually at virtually minimum load at only 120 kilowatts. We had inlet dampers as well. The fan was also on a VSD. Now obviously, so this 315 kilowatt fan is fitted with a 315 kilowatt VSD, rather large cables and everything else. Now because the fan was running so slowly, the efficiency was way down. They had to use a secondary control valve just to put enough static pressure into the system to actually load everything up. And so actually of the 120 kilowatts, a big chunk of it was just being wasted just to have the system stable. And so, you know, what was the opportunity here with this system? Well, in real simple terms, the thing that needed to change was the fan was actually too big. And so the question arises, well, okay, is it that we just need to run the system a lot harder and do a lot more, and is that potentially an option? And it may well be. Alternately, if everything is just being grossly oversized, we can do one of two things. We can actually change the impeller. We could trim it or do an actual smaller impeller. We could reduce the width of the impeller as well as just the diameter. We could then look at removing the primary control valve and the inlet dampers. Then even still, we may still need VSD control. But ultimately, there's some options to consider where everything can be more correctly sized for the load and duty that it needs. It may be that we need to redesign the process. It could be that we can get a lot more out of that process. There might be another bottleneck further down that if we undo that bottleneck, then everything else, we can then untap that unrealized capacity. Now, once this is all done, of course, you'd probably need to look at replacing the motor, the VSD. Now, of course, what happens is if this is a system, you think, well, it's already in there, does it really matter? Well, long term, if you take the bigger picture considerations here, a fan that's that lightly loaded is probably going to have trouble with its bearings as well. Bearings can also fail due to being underloaded. There are other maintenance implications here. Now, of course, if you don't need a motor that big, obviously carrying a spare to be able to change out becomes very expensive. Likewise, VSDs and so forth. If you can consolidate, you might not go to the smallest motor available, but thinking about how you can consolidate and rationalise what you might need to keep in terms of spare parts could also be useful. Now, in this particular application, there was about 20% power savings, which was over $20,000 per annum. But the big opportunity that they were able to realise in this particular instance by debottlenecking other parts of the process was also realising a significant capacity increase. And just to give us some sort of context here, that capacity increase was in the hundreds of thousands of dollars per annum. And so this is just a really good reminder that, okay, there's some good energy savings on the table, but what else is also important is some of these other indirect benefits can be substantially larger and orders of magnitude larger. Okay, so just had another very good question from Ben. Let's see, Ben. Are you mic'd up, Ben?
No.
There you go. I can hear you.
Oh, yeah.
So just let me make sure I've got your question right here, Ben. You're saying with an impeller change, what does the impeller angle do to the tuning, correct?
Correct.
Yeah, so I guess this depends if you're talking about an axial fan versus sort of a centrifugal fan. So to be fair, what I'm talking about here in terms of an impeller trim or an impeller change is typically you're still going to stay with the same type of fan. So certainly, obviously, with an axial fan, you might have a variable pitch fan which you can adjust, and that's a great means of control. It really does depend on the pressure flow sort of mix that you're looking for. But typically what we'd be talking about in saying, look, if the impeller's undersized or oversized, you're going to be not so much necessarily changing fan type, but more just getting the right sized impeller. Now, in some extreme cases, yes, you might actually be using the wrong type of fan, in which case the solution is actually to change types of fan. But typically, if you are going to do that, an axial fan is going to take a completely different installation to, say, a centrifugal fan.
Okay.
So it really depends on the application, but this is where, like I said a few minutes ago, if you're really getting into this space, having a very good relationship with a good quality fan supplier becomes important, because obviously assuming that you've done some good system measurements, you're going to know what sort of flows and pressures you want, i.e. you're going to know what your system curve is, and then it may be, well, actually my fan curve is nothing close to what I need in practice, and so that might need to be changed. But in real simple terms, typically a minor trim, you'll literally just take a little bit off the existing impeller. If it's a little bit more substantial, then it might be just a straight impeller replacement. That can be done relatively quickly. Often that's sort of less than a one-day shut if everything's all prepared in advance. And likewise, obviously, if you're looking to change the width of the impeller, often that would be a straight impeller swap as well, as opposed to physically taking the impeller out, mounting it in a lathe and machining a bit off. Obviously, actual fans slightly different in that you've got to start thinking a little bit more carefully about the whole shape and design of the blades and so forth. Yeah, so has that sort of answered your question, or do you have anything else you want to add to that?
No, that's good. Thanks, James.
No, appreciate it. All right, I'll continue with the webinar, but hey, appreciate the input there, Ben. Great, relevant question. Okay, so what we'll do now is moving on. We're going to now look at multiple outlet situation. So here we have, in this particular instance, it was a 110 kilowatt fan. So single fan again with multiple outlets. Now what of course was interesting here is we had a number of control points. So we had a primary control damper valve. and then we had a secondary damper valve on the 3 parallel outlets, and then of course the fan was also fitted with the VSD. Now in this particular instance, funnily enough, the VSD was left running at 100%, so actually the VSD was introducing a number of additional modes of failure to the system from a maintenance and reliability point of view, adding a whole heap of capital cost and costing about an extra 3% in energy without providing any real value. So really not an ideal situation. Now with that initial setup, they were pulling nearly 8,000 pascals, fan was running at 60 kilowatts. That tells me straight away the fan was massively underloaded compared to what it was rated to do, and to obviously get it to run, we've put a massive static load on it to wind it back. Our inlet delta P was 600 pascals, the heat exchanger delta P was only 250 pascals, we were losing nearly 3,000 pascals across the control valves, and the process actually only needed 4 kPa. And so it was sort of quite a wasteful system, but the philosophy was, well look, we need to control and get an even flow across each of these outlets. Now of course what was interesting is because we had a relatively high process load in terms of the static pressure, there was more than enough static pressure to ensure that the flow was evenly distributed without those secondary control valves. So those secondary control valves could be completely removed. Clearly the fan was oversized for its duty. We could get rid of the primary control valve after the fan, revert to VSD control. The secondary flow control valves weren't needed either, and so basically we were pulling about 45,000 per annum, but as it turns out this particular part of the process was one of the major bottlenecks. And so what we ended up doing, because of course the philosophy was the fan's at full speed, it's at 100%, we've got nothing more to give, therefore we're stuck, it's a bottleneck. Well, when we looked at the system and had a bit of a closer look and started to tune and figure out what we could do, by removing those additional control valves and reverting to VSD control, okay, we dropped the total static pressure, actually dropped quite substantially to under 4,000 pascals, because what we found we could also do was reduce the pressure drop across the actual process by getting the flow right, by not disturbing the flow upstream of those outlets. You'll recall a few slides ago we talked about how whenever we have these dampers they can disturb the flow and cause downstream effects. What they thought was a 4,000 pascal load was less than 3,000 pascals, and that was simply by improving the airflow, by not having that disturbance from the control valve. So kind of ironic, the very thing that they thought they were using to control and help the system was actually doing more harm than good. So pulling that out, not only did we save pressure, save energy, it actually improved the performance of the process, became a lot more even, the product quality went up with the product they were making. Now of course what happened is the fan power dropped to under 40 kilowatts, so we were saving over 50%. Now if you are replicating this in a new build of course, which is one of the things we looked at for the customer, obviously that fan and motor, VSD cables, everything could be substantially smaller. Big step up in size in terms of capital spend, going from sort of say 37 kilowatt fan, cable and VSD compared to sort of 110 kilowatt option. Now even within all of that, plenty of opportunity to actually add additional capacity to the process. So just another example where just because we have multiple outlets, it doesn't mean that we need to throttle those all to get them even. There's some smarter ways to do it. Now being in New Zealand, we do a lot of work with the dairy industry, and when it comes to fan systems, these big spray dryers are a magnificent case study to keep on going back to. And so we're going to talk a little bit about a spray dryer. This is just looking into the top of one of these buildings as they're built. They move a lot of airflow around. Typically on the front there will be possibly some preheat and some filtration, a fan, and then a heating, then sort of a drying chamber, exhaust cyclones, exhaust fans, and possibly damper valves and the like. Now of course as we come in we've got a number of losses across the inlet, obviously a pressure rise from an inlet fan, a bit more of a loss across a heater, then typically these dryer chambers are under a slight vacuum. Then obviously we have an exhaust system and then typically an exhaust fan. Now, what will happen in practice is we might have more than one fan supplying the inlet. There could be secondary air coming in from the bottom, and it's quite common to see multiple exhaust fans in parallel. So a combination of fans in series and parallel, and looking at how they're controlled. So we have multiple control points. Common that these fans are fitted with VSDs. Not uncommon to also have flow dampers and inlet guide vanes and the like in these systems. Often they have both of those. Additional isolation knives that come down to block off certain parts of the plant when they get cleaned. Now, if you're looking at a system like this or some other system that might be a little different but can follow the same principles, as a starting point, what you want to do is you've got to understand, well, where are my control points in the system and what does each control point actually do? So for example, if we go back here previously, the exhaust fans on a system like this will typically be controlling a pressure in our chamber, or it might be a reaction vessel depending on the industry you're in. But so your exhaust fan will be controlling typically to regulate or maintain a certain pressure. You will then have an inlet fan that will be controlling to a certain inlet feed. You then might have a steam control valve which is controlling a temperature of that feed. And then you will have some other reaction feed. In this case you might have a concentrate going to the dryer that will then be regulating the outlet temperature. And so what you'll have in your system is you'll have multiple variables all being controlled by separate systems that may be coupled, or they could be quite independent. Now, of course, what happens as you increase a feed of airflow, assuming you've got a heat exchanger and you're controlling to a temperature, you're going to change the energy going in. As you change the energy going in, if you're controlling to an outlet temperature with what you're feeding into your reaction vessel, then that's going to change your feed there. Then of course all of that's going to change your pressure, and so therefore your exhaust fan's going to change. And so all these variables are all going to interact. They are all going to be coupled. It's not always linear. So it's very, very important before you start to play with a system like this or think that you're going to tune it, that you understand the control loop. Now, the control loop I've just gone through for a spray dryer may not be the control loop on your plant, even though it's a spray dryer. It could have quite a different loop. Over the years, there's been a number of different variety of systems used and dabbled with. Some work a little better than others. But the key thing to remember if you're starting down this path is A, understand what your control levers are. B, understand that when you pull that lever you should know in advance what's going to happen. And then as you do that you should be able to know what it is you need to measure to be able to determine whether what you're doing is heading in the right direction or the wrong direction. It's very important that when you look at something like this that you understand that there is an overall system and then the individual system. So like the air heater will be a little subsystem that you might be able to optimize, but when you're doing that you need to keep an eye on what that may have in terms of an impact on the overall system. So the other thing to think about is you might have other external control variables that may actually not be under control. So for example, your main inlet temperature and humidity outside, those of you in sort of the food industry or even pulp and paper, any of those sectors where you're drying a product, as you go through the year, your ambient conditions outside can change dramatically, both in temperature and humidity, which is going to change the performance of your plant, which is then going to change how you run it, how you control it. And so it's not only understanding tuning the system based on today's conditions, but having an appreciation of how those conditions might change both through the day, through the week, and then through the year. So very, very important to understand the context of what it is you're doing. So it's very, very easy to come in and think, right, I can, James has said we can save some money if we tweak this fan, we do this, we do that. fantastic, we've just saved $30,000 a year in energy, only to find out that you've compromised the performance of the process, the quality of the product is not what it should be, the capacity of the plant is no longer what it should be, and it's very easy that you've saved $20,000 per annum in energy and cost yourselves $500,000 in other areas. So very, very important that you look at the bigger picture when you come to look at actually tuning the system. Having said that, I hope I haven't scared you off looking at this, but it's just a good reminder to remember that that's what we need to always be thinking about when we start to look at the bigger picture. So here's an example of a dryer where you've got multiple fans feeding in, and then obviously an exhaust fan here out. It could be that there's multiple exhaust streams coming out. So once again, just remembering we need to be mindful that we've got or may have multiple inlets and outlet streams that you need to manage. Okay, and remembering that each control point serves a specific purpose. And then once you understand how those things are working correctly, we can then start to look at, can we eliminate a number of multiple flow dampers, for example? Have we got fixed dampers tuned correctly? Is everything where it should be? Have we got extra blockages in the system that we shouldn't have? Are there things there that are impacting on the performance of our system that we can look to retweak? So when we look at sort of tuning up these systems, the things to sort of look for, can I simplify my primary control points? Have we got a VSD or an inlet damper or a control valve? We do not want to duplicate. And just a reminder on this point, we see this over and over again where damper valves are installed on a basis of we need to isolate the system for this or for that and so on. Remembering that if you do need these isolation points, they can be zero loss. They can be engineered so that they don't actually have anything in the way of the airflow when you're running, as opposed to having big butterfly valves that very easily might not be fully open, and if they are open they could actually cause problems. And we've got some examples I'll show you in just a minute where even though you think it's okay, my butterfly's open at 100%, therefore it's not disturbing the flow, it may well be, and we'll show you an example of that in just a minute. Just to reiterate, if you've got secondary flow control valves, butterfly valves, dampers and the like, looking at trying to retune them, or if possible eliminating them, can be a huge gain to your system. Understand that your system or your reaction vessel, your fluidized bed or whatever it is where that has these multiple inlets, typically is going to have a reasonable pressure drop across it, and in most cases that pressure drop is more than sufficient to ensure adequate uniform flow without having additional dampers, which often you'll get operators playing with and tweaking with and doing more harm than good. And often if you a little bit of attention to detail on the airflow upstream of how this air is distributed across multiple inlets, getting good duct design, good layout of that is far more effective in the long run than having all these multiple secondary control valves that can be tweaked and played with. And so you can go through and tune the whole system only to find that an operator on night shift had all the best intentions in the world of improving things, thought he'd have a go, and in many cases it can end in disaster, and then you've got to start all over again. So sometimes a process redesign might be required where we can lower our static pressure drop, we can streamline the airflow. It's not uncommon at all in many of these industrial systems to have a 20 to 30% reduction in fan power, which can often also realise opportunities to increase the plant or process capacity. Now in all of this, generally what you will find, if you get better airflow, more uniform airflow, you're also going to improve the performance of your system in terms of quality, stability, control, and so forth. Now here's a really good example. We've got a duct here. On the figure to the right, the flow is coming around the corner and coming in here into a vessel. This is just looking at the slice through the flow coming around the corner here. And then we have a butterfly valve that is open at 100%, therefore it's not going to disturb the flow. But what you're seeing here is the duct is coming down at an angle and coming around a corner. Now what of course happens is we probably, to be fair, don't want the butterfly vertical here, because what that will happen is that will segregate the high velocity zone, which is your reds and your yellows in the picture over here, are all on this side. So if I just change color here and go with a pen, the last thing we want is the butterfly vertically, because that's going to segregate the flow on one side and not allow it to expand at all. However, what you'll notice is that coming around the corner here, you still get some segregation on one side versus the other. And of course, if this is a fluidized bed where the flow's going to come in and go up, if it's all heading down and that butterfly valve is there horizontally, that is going to stop the flow from wanting to come up and go up here. It's going to tend to stratify the flow and have it all coming down below. So really, really important to understand where your flow is going and understanding how damper valves can actually be doing more harm than good, even if they are open 100%. So here's another really good example. Now this is, I haven't shown the picture here, but in the middle here was a rather large fluidized bed, and it was being fed from both sides. So this was a common inlet duct at the top that split in two, fed down both sides, and then coming in from either side. And you'll notice that actually on each side there were two outlets that was further divided. Now what we have here, just to give you an indication of what was there, we also had a vertical butterfly valve in here and another one in here, and these were isolation valves as opposed to primary control valves. Now what of course happened in the first instance, you'll notice that flow is trying to come down here and around the corner, and if we draw that on here, you can see we've immediately got a problem. Now what of course happened is this system was on a VSD. VSD was left at 100% because they couldn't balance the airflow across the two sides. Now of course, why couldn't they balance the two airflows? Well, of course the damper valve on this side that was actuating was actually aiding the flow around this bend, whereas this damper valve here was actually, the flow was fighting against the bend. And so lo and beside, despite their best efforts, the left-hand side of the system got substantially more airflow than the right. Now of course, the first thing we wanted to do was balance the airflow. What we were able to do was actually, it was costly to pull those valves out. So we said, look, okay, let's leave them in just to start with. So they were left open at 100%. And so if we just rub those lines out for you. And so what we ended up doing is that valve was then running vertically like so, so it was a lot more neutral. And then what we were able to do was with the VSD tune everything down, and we had the airflow on both sides balanced with just purely VSD control with a flow meter, even on both sides, to within less than 1% variation. So quite successful and effective compared to, I think it was a sort of a 25% imbalance between the two previously. What that was also able to do was save about $60,000 per annum in power savings. Now why I want to also draw your attention here though is there were a few other little issues in a system like this. That was the easy part. What you'll notice is the air is coming down here, and then it's having to turn here, then go this way, and then this way. Now of course air, as those of you that have listened to a number of our webinars now will know, air doesn't turn 90-degree bends very well at all. And of course what's going to happen here, if we look in plan view, we'll just erase that. In plan view, flow's coming down, doing this and doing this. Of course, if I've got a butterfly valve here in my duct, so let's just have our duct come here like this. If I've got a butterfly valve through here, my flow's actually not going to go on a right angle. It's going to want to come and do this. And so it's going to do this, and it's going to come through here and not through the other side. And so these butterfly valves, even open at 100%, is going to disturb the flow and ruin the distribution of airflow across my system. In this case, it was a fluidized bed. So really, really important that we get this sort of thing right. and its attention to detail. So ultimately, what did we learn from this particular exercise and case study? Well, correct placement and use of damper vanes is very, very important. Good flow isn't going to happen by accident. The air does not change direction very well. We need to understand the impact of multiple out-of-plane bends. So that was the bends we were just talking about. And balance flow, so we've got balance flow by taking out those damper vanes and using the VSD to control the airflow. However, what it didn't do was give us uniform flow across the actual bed itself, and so we had to take additional steps to realise the full potential of optimising the system. So as you go through, you can systematically eliminate these defects in the system, and then as you do that, you can realise the benefits. So to summarise, we have a number of key system tuning KPIs that we need to worry about, and the first one is stability and stable control. So we need to be able to have stable control of our flows, and then by default obviously temperatures, humidities and so forth, and then obviously be able to know that we can get them consistent, get them balanced. Obviously part of that, then we want to minimise our static pressure loss through our system. As we do all of that, we should get balanced flow across any situations where we have multiple inlets or outlets. And then as we do that, we can then look to have uniform flow distribution across our reaction vessels, fluid beds, etc. And if we do that, we'll then get benefits in terms of better uniformity in our product that we're making, tighter controls on the specification or functional properties of whatever product we might be making, better quality metrics and so forth. But very, very important that it's very much a hierarchy, and it starts with stable and sound control, minimizing our losses, and then getting our balance and distribution right. Okay, so similar sort of principles can be applied to boilers and burners. So a number of times we've talked with people and been asked to look at boilers where they keep having someone come and tune the boiler, and only to find that that's great, but then other things change, and because in tuning the boiler they've looked more at the fuel side as opposed to the air side. If there's an imbalance on the air side, then if you don't address that, you're going to struggle to get a good performance out of your boiler. So very important in terms of solid fuel boilers to get good airflow distribution. Gas boilers generally, by their very nature of their design in terms of the burner heads and all the rest of it, they being an integrated unit, they generally should be pretty good and not such an issue. But on your solid fuel boiler, if you have one, very, very important to get your airflow distribution across your drape just right. When you've got common exhaust across multiple boilers, need to make sure that you get that right, that you don't cause issues with systems coming on and off. Very important to get your flow dampers or guide vanes in the right spot. If you're using VSDs, making sure that you're using them correctly. And when you are tuning the boiler, are you actually looking at the whole system? Are you looking at the air side as well as the fuel side? Are you getting it right? Do you understand how the system curve on the air side changes as you get a build-up of soot and other material or debris, my apologies, through running the system? Is there something you need to do to tweak to adjust your airflow accordingly? So remember that the fan costs on these systems are going to be much, much smaller than your fuel cost, but it means that the fans should still be looked at, because those fans are going to have a massive impact potentially on the efficiency and performance of your system, even though they might not be considered the primary cost center if you're worrying about your boiler. It's very easy to ignore, and they're often the root cause of many of your problems. Okay, so what we want to do to finish up today is to really cover off some of the spillover benefits that come from good system tuning. So yes, there's energy efficiency, but often more important and more valuable, and it certainly helps you to get buy-in from other parts of your company or business, is better process control, better stability, better process and equipment reliability. Often you'll have reduced startup times, generally better quality, better yield, and often a chance to get better plant capacity. Now, in the context of all of this, it's very important to remember that you need to understand what your system constraints are. Then, of course, what happens if you relax them? So any good optimization process all comes down to understanding your constraints and what your limits are, and understanding that as you relax those various constraints, what happens. Now, as you work your way through all of this, and then as you do your various tests, assuming that you're able to, what you should be able to determine is what are the limiting constraints. Is there a temperature limit? Is there a humidity limit? Is there a flow rate limit? Is there a water removal or evaporation limit? Is there some other product functionality or specification or quality metric that we need to sustain, and that might actually put a limit on how far you can reduce things. Reducing airflow might save you some energy, or increasing airflow could give you more capacity and then give you better specific energy, but there will be a limit to how far you want to push that before you run into trouble, because it might then compromise some of these other metrics. And so we're going to show you an example in just a minute, but just to reiterate, as you go through and tune a system, if it's well tuned, you could look to see minimum static pressures, uniform flow distributions. You should have minimal unsteady turbulence in your flows, which will give you minimal vibration, minimal noise, which we talked a little bit about earlier today. You're ultimately going to have less load on rotating equipment, and in most cases that's going to be a good thing. I say most because occasionally with modern systems, actually underloading equipment can be a challenge. So very important that you're mindful of that. Could be a problem. But typically less load on rotating equipment is a good thing. You might free up spare capacity. But the other thing to think about here is you've got the unit operation efficiency gain that you might get from having a fan running more efficiently, or a heater or a reactor running more effectively. However, what you need to remember is it's the overall performance of the system that ultimately matters. Now, here's a really good example. I can't go into too many details, but here's a system where we had a range of airflows, and you can see there's sort of quite a performance there, and then there's sort of a bit of a peak in here. Then what you'll see is there's a pressure drop as a part of your system in terms of a cyclone, which was a key separation vessel in this process. You can see your fan powers both on the inlet and the exhaust. You can see that we sort of had an imbalance, and as we come down and we get the system into control, everything's looking really nice. Now what's interesting is this bottom curve here is actually an evaporation rate. So if you think about this big arch here, this is effectively capacity of the plant. And what you can see is the energy drawn by the plant was quite dramatic as we come back down here. So there's sort of about 140 kilowatts of savings coming from here to there with the same production. Now in the middle actually there's a bit of a production increase. Now what you need to be mindful of is superimposed over this we've got some other metrics. The quality of the powder here might not be too good, or the product that you're making, whereas the quality here is very good. So somewhere in between here is a limit that we probably want to hit up against. So we probably don't want to be there, we probably don't want to be here. We've got to find that sweet spot of where we're getting the overall balance of what we want out of the system. So it's very, very important to understand that there's multiple variables that you're optimizing, and that some of them will be hard constraints that will be non-negotiable, and then within that you then need to determine where it is that you want to operate. Now just to summarize that in some real simple but generic terms, you need to be thinking in terms of your quality metrics of whatever it is you're making. The other thing to think about is there's some plant downtime considerations. You might be running the system really well, but it might mean that there's a lot more cleaning required, or there's a lot more build-up of product, which means your yields might be down a little bit. You might have increased maintenance requirements because of duties or loads on things. Extra cleaning might have other side effects. So it's important to understand that there are other things in the mix that we need to satisfy here. And aside from all of those metrics, there might be specific specifications for the product you're making, not just efficiency, that you need to satisfy. It might be that if you can meet some of those specifications, you can sell a higher value product, which can get a premium in the marketplace. So very, very important to understand what you can and can't do and what you're not prepared to compromise on. The other thing, of course, is you might think, oh, look, the product's okay, it needs a bit of rework, we can blend it in and that's all okay. But all of that comes at a cost. So for example, when you start up your process, the first little bit might need to be reblended because it's not quite within spec. So obviously if you make these changes, get the system more stable, it's not uncommon to see startup times drop from a couple of hours to sort of 20 minutes. Well, depending on the size of your production line, that extra hour and a half of production of being reblended as opposed to first time grade product can be quite a saving in and of itself. So really, really important to understand the bigger picture here. Now for you to actually really do this in practice, you need to understand the whole process, which typically is going to require a multidisciplinary team approach, meaning that you as the energy guy or the maintenance guy, you're not going to do this on your own. You're going to need to have other people get involved. You're going to need some operations guys. You might see some technical guys. There's a whole range of people that will need to be engaged. Now, the advantage of doing that, of course, is you then get them engaged in the process. You're starting to help them improve some of their KPIs, and before you know it, you've got the whole business engaged and you can embark on this journey together. And ultimately, every single time after time, a whole of system approach where you're looking to optimize the system is going to deliver bigger gains and more long-term gains for the business, and the ability to lock those in for the long term are going to be substantially more likely. So in summary, to finish off today, is you want to identify any duplication of control. Where you've got VSDs plus other primary or secondary control dampers, have a close hard look at that. Are they all necessary? Can we get some improvements by rationalizing them? Do I need to change my fan? Is my fan too big? Is it a pulley change? Is it a VSD, or do I need to actually look at my impeller? The indicators to think about is your system efficiency, your fan efficiency. Have I got secondary flow control dampers with high turn down? Okay. Poor airflow downstream from control points is a telltale sign that we perhaps need to look at how we're controlling things to actually improve our process. It's not uncommon for a system tune-up to give you a 30% saving or more. I know it's sort of a bit cliche to sort of talk about these sorts of numbers, but if you're sitting there today and thinking, well, gee, you know, what's in it for me? Is there something I should be looking at? Well, have a look at what you're spending on all your fans and turn around and run the numbers and say, look, if I can get 20-30% off that, what's that worth to me? That gives you a ballpark figure straight away as to whether it's worth looking at. The other way to look at it, of course, is okay, let's say we have a lot of outages, you know, a lot of downtime because of this, because of that. Ask yourself this question: if I could cut my outages in half, what's that worth to the business? And then have a look at that, and surely, you know, with a bit of a problem solve and delving into try and identify what some of these issues are, even if you can stop half of those downtime outages as opposed to all of them, what's that worth? And you'd be surprised at just how much money is potentially sitting on the table. Now there could be other indirect process benefits from better airflow in terms of quality and reliability and stability and so forth. But just to reiterate the final point today, whole of system optimization is critical. If you start to look at the whole system, you're then under the way of getting there and getting the relevant people on board. Okay, so that really concludes our webinar today. We're going to stay on the line for a few minutes to answer any more questions that you might have. Appreciate the questions that we had as we went through today. Just a reminder, webinars coming up between now and Christmas. So watch out for your inbox for these invites as they come out over the next couple of weeks. So we've got pumps and cavitation on the 19th, so in 2 weeks' time. Then we're going to have a look at steam traps on the 2nd of November. Then a follow-up in terms of heat exchange and network, looking at retrofits with Tim. And then to finish off the year, we're going to be looking at energy metering and monitoring, and then looking at how we translate that into benchmarks and targets in the 14th of December with Martin. So as always, a reminder that we will have in the next few weeks the registration links up on our website. and the past webinars are available on the EcoBusiness YouTube channel. Okay, very good question, Christo. Let's see if Christo's mic'd up. Christo, are you mic'd up there, mate? You there, Christo? No mic? Okay, that's all right. Hey, excellent question from Christo here. What he said is there a recommended maximum fan tip speed which one should adhere to, applicable when increasing fan speed? Very good question, and you'll recall that when we talked about this a little bit earlier, we talked about the importance of having a good relationship with your fan supplier. And what you need to be very, very careful of is depending on the construction of the fan, there will be a maximum rotational speed for an impeller, and that's a function of the material that the impeller's made of, in terms of the stresses in the impeller may get to the point where the thing will catastrophically fail, and that could be quite sudden and catastrophic, quite destructive, and take quite a bit of collateral damage with it. So very, very important. There will be recommended running speeds, and there will be rated maximum speeds. If you have a reputable fan, or a fan from a reputable supplier on the nameplate, in addition to the motor rating and the nameplate rating of the fan in terms of pressure and flow, it should have on there a rated fan speed for that nominal output, and on a separate item there on the nameplate it should have a maximum recommended rotor speed. Now, it is fair to say that in certain situations that maximum rotor speed or impeller speed could be increased on inspection of the impeller. However, you want to do that very, very carefully, and what we generally recommend to people, if you're looking at doing this, you get your fan supplier to come and do an inspection of the running gear on the fan itself. There's a number of things to look at. For example, the rating of the bearings, the load on the bearings. There will be a maximum speed limit on the bearings as well. There will be a load limit on the bearings. There'll be vibration limits. All of these things need to be checked off. There's not a hard and fast single maximum speed. It depends on the nature of the impeller. Ultimately, there is an upper bound where the tip speed, as you speed the fan up, going faster and faster, things are going to start to effectively stall. If you think about the blades on a backward curved centrifugal fan are typically little aerofoils. You can imagine you'll get to a point as those like a wing on an aeroplane will get to some point where they're going to stall, and you can spin them faster and faster and faster. It's going to get to a point where it just can't suck the air in that it needs, and so then flow is going to collapse and the performance of the fan is going to drop off. So all of these come into the mix, and so it does depend on a case-by-case basis. To give you an idea, for example, there are some HVAC fans that might have a maximum speed of, say, 600 RPM, and then there's some sort of process fans that might happily run to over 3,000 RPM. So there's not a single hard and fast number. It's sort of a question of understanding the application, understanding the nature of the fan. Now, if you're absolutely desperate for just that little bit more capacity, but you don't want to pull out, the whole fan housing and all the rest of it, there's a couple of different options you can look at, and one of them might be is you could commission a new higher spec impeller that will be made out of stronger material. It might have a stronger backing plate, for example, might have additional gussets for support, but fundamentally these impellers can be designed to be run at a higher speed, and so you can get more output. Now, as you do that, of course, your fan power is going to go up, and so you might need to also then replace a motor. But typically in many a retrofit situation, a new impeller, a new motor can be a very cost-effective solution as opposed to a complete rebuild of the process. So really does depend in terms of the application, but very, very important to understand that there are limits as you speed things up, and you need to be very, very careful how you do that, especially if you've got older equipment. where that equipment should probably be inspected to ensure that it's actually of a sufficient standard and quality to be sped up. So hopefully that's answered your question, Christo. I'm happy to stay on the line for a few more minutes if anyone else has any questions. Failing that, a reminder that the webinar recording will be available to share with people or colleagues that may have missed today's presentation. And like I said, we'll be joining us again in 2 weeks' time for the pump cavitation webinar. Okay, so looks like everyone's quite happy there for today. If you do have questions that maybe you're a little shy and you don't want to have me put you on the spot, by all means feel free to send me an email at jamesn@waikato.ac.nz. And what you can also do is just remember that you can get some help from your ECA account representative. Is also available to assist. There's some resources available on the ECA website. And then of course, just a reminder, there are some great fan source books available on the internet. They're all freely available as a download. That's some useful material. Doesn't get into as much detail around some of the things we've talked about today, but they are still a good source to remind ourselves of some of the do's and don'ts as we are trying to fiddle with fans and so forth. So look, thanks very much for joining us today, and we look forward to seeing you again in 2 weeks' time. And until then, and stay safe, and all the best with your projects and finding opportunities to save energy and improve the performance of your system.